Hey everybody, hello, I'm Yasin. Sorry for the small delay. We are experiencing a bit of technical difficulties with our speaker today, so hence why there has been a delay, and we're still trying to resolve these issues. So we'll kick off with a really small delay, but up until then, hopefully we can discuss some of the things that you guys might want to be to share, like things that you will be working on or ideas that you might have. So in any case, I would like to welcome you all. Feel free to use the chat section and the question section to ask any questions that you might have. Say hi, obviously. So good morning, good evening, good afternoon, wherever you are. Feel free to say where you're all coming from, and I'd love to read what you're all planning for this hackathon. And in the meantime, hopefully our speaker will be able to resolve the technical issues on their end, so we can kick things off. Today's topic is going to be about the tokenization of latent computing power, and it's going to be done by CoopHive. So hopefully that's going to kick off real soon as the speaker resolves the speaker issues. The technical issues. In the meantime, as I said, I would love to know what you're all building on. So feel free to share in the chat. And from what I can see, I think our speaker just joined. So just want to add you on stage, and maybe we can get the party going.
Hey.
Hey.
Can you see me?
Yes, we can all hear you, or the audience as well. Everyone say hi to Levi. He's going to be our speaker today. As I said, the topic for today is going to be about tokenization of latent computing power. So yeah, Levi, feel free to say hi, introduce yourself, and yeah, take it away.
Hey everyone. Thank you so much, Yasin. Hi, my name is Levi. I'm the founder of CoopHive. Let's just jump right into it. CoopHive is a two-sided marketplace for compute at its core. It connects clients and compute nodes, basically I'll kind of go into the details just a tiny bit, so because you're going to be hacking on this. So we basically have people who need compute, people who have compute. The people who have compute say to a entity known as the solver, which is kind of like a market maker, saying, I have this compute. The people who need compute say, I need this compute. They also say it to that solver. The solver acts as a market maker. It does some kind of matching algorithm. It proposes a deal to the two sides. If the two sides agree, then they form a deal, and that deal is put onto IPFS, and the CID is posted on chain. That's going to be very important, and I'll mention why. Then the compute node computes the result. The result is put onto IPFS, and then the CID is also put on chain. And then there's an arbitrary mediation protocol, which can be used to check whether the result was done correctly or not. And then the result of if that happens, the result of that is put onto IPFS, and the CID is put on chain. And I'm assuming familiarity with IPFS here. For those of you who don't know, IPFS is interplanetary file system. It is a content address file system. So you look up things by what they are, not where they are. So when you go into your regular URL browser, you do http://. That is where you're looking up data by where it is. In IPFS, you look it up by what it is, which is its hash, which is immutable, right? It doesn't change. And so why is that important? Basically, what we end up with on-chain is basically a sequence of IPFS CIDs, which for us just act as pointers to off-chain data. So what we have is a rule set for taking, for putting just these kind of hashes on-chain, these really, really lightweight data structures, which can point to kind of arbitrarily complex off-chain data structures. And that facilitates for us right now marketplace. Actually, it can accomplish a lot more. We won't have time to get into that. To all of the applications today, we'll get into one of them. Basically, two-sided marketplace for compute. You keep a track record of the deals, the results, and the mediations on chain, and then the payments and collateralization and so on are mediated by smart contracts. That's basically the TLDR of how CoopHive works. Now, what is the challenge, the bounty challenge? I think everyone here would be very interested in that. So basically, the challenge is about the tokenization of latent computing power. So all around us, on your laptop, or your desktop, on your phone, on IoT devices everywhere, sensors, cameras, GPU servers and data centers, really everywhere that you can think of. There's always some amount of slack of spare computing capacity that just isn't being used. It's just sitting around and doing nothing. Now, in some cases, you kind of need that slack, like in some data centers, for example. But in a lot of cases, there's just all this like enormous potential, this computational potential out there, which can produce an enormous amount of value, but just isn't being used properly. And so the question is, can we make better use of it than it's just sitting around idly and not doing anything at all? And so that really leads us to the question of, can we find computations that nobody's willing to pay for now, but that somebody might be willing to pay for later, right? So let's give an example. Suppose that you think that you have the cure for cancer. You need a ton of compute.
I've received a question on private. People asking whether you have slides that you can share. Like they don't know if you're speaking from slides they're not seeing, or
I'm not speaking from slides. Okay. Yes. I'm living the true founder life of working morning till night, and I have not had time to prepare slides. I'm very sorry. Although I'm happy to provide you with, if you can direct them my way, I'm happy to provide like supplementary material. We do have diagrams. I mean, I can give you. This is actually an outdated white paper, but because I'm actually writing the new one right now. But our old white paper does actually have. So here's an architecture. It doesn't actually have the IPFS stuff in there, although I do have that elsewhere that I can share. But yeah, I'm just going to post these in the chat. So that's our architecture. And let me just give you our white paper. This is our white paper. And so if you go to page... where is it? I think the bottom of page 5 starts talking about CoopHive, and then like the bottom of like bottom of page 6, top of page 7 starts going into like the details basically, and that should give you a much more in-depth view of like how this works, what a job life cycle looks like, how the smart contracts are structured, how the job offers and resource offers are structured, how market making works, collateralization, all that stuff. So all of that is in those two links I just shared. Right. So tokenization, yes. So tokenization of latent computing power. Suppose you think you have the cure for cancer. You need a ton of computational power for it, but you don't have the money and you don't have the compute. So what do? Well, you can go up, and I'm going to pause here and give a bit of history. Back in the late 90s, there was this project called SETI at Home, which stood for the Search for Extraterrestrial Intelligence at Home. Basically, what a bunch of scientists did was that they took data from radio telescopes. Oh, were you part of it? Did you do it? Nice. Okay, so yes, and it's perfect. It was very popular. I think millions of people back in the day. Like it was very, very popular. So these scientists, were taking data from radio telescopes, and they wanted to look for aliens. But like it's a lot of data, and they just didn't have the computational resources for it. So they took this data and they spread it out to all these nodes all around the world, and these nodes computed the data locally, and then they returned the results to the central server. And they basically just did it was volunteer computing. And out of SETI at Home grew BOINC, which is just the Berkeley Open Infrastructure for Network Computing. They just had their workshop in Geneva a few days ago, 20th anniversary. And they applied that same model to many different types of computations. Mapping the Milky, making a three-dimensional map of the Milky Way, looking for prime numbers. Finding the spike protein for COVID, which happened in the beginning of 2020. It was tons of computational projects centered around this idea that people can go and contribute a free computing power to scientists who are in need of it. And then, of course, folding at home, which is another one that was focused on protein dynamics and protein folding, et cetera. There's another massive one, kind of SETI at home level size. Going back to our cure for cancer situation, well, you can do the same thing, right? We can go up to this network of nodes and say, hey, if you compute this, we'll keep a track record of what you did. If something comes out of it, now we can tokenize it, right? Before in SETI at Home and BOINC and folding at home, we got Web2 bounding points, basically. But in Web3, you can actually tokenize this, right? And which opens up a huge number of possibilities, right? Because once you tokenize it, you can put it on the market. And that just enables all sorts of like fascinating use cases that we'll get into momentarily. So basically, you keep a track record, and also very important to keep in mind. I'm going to go on a bunch of little side rails here. In SETI at home, and folding at home, and in Boink, you have the traditional client-server model, right? There's a client. I need to send out a computation. The server does the computation and sends the result back to me. When we're in Web3, we know what happens. We don't really have that client-server model as much anymore because we can take the data and store it in a decentralized manner, right? Before, the only people who could really truly make sure that the data is reproducible, that the computations are reproducible, that we know that we're getting the right results, were the scientists who held that server. And it was just fine because those scientists were trustworthy and they were doing the right thing. But when we're in Web3, there's a bit, we're supposed to be trustless and permissionless, right? So what we can do is we can take that data and spread it around a bunch of different nodes in decentralized decentralized databases. So like there's just, for example, Tableland, Orbis, there's a bunch more. And so we can actually make sure that anybody can come along and reproduce the results, right? And which is really beneficial because we have this massive, massive problem in science called the replication crisis. Tons of scientific studies are not replicable. And it's not just in the social sciences, it's a bit of a misconception. There's a lot of stuff that relies on computations where the scientists won't even give up the data sets, won't give up the code, or won't release it open source. And when they have the ability. In some cases, there was a big thing, I think a year ago or something, where a ton of scientists who said that they would give up the data or open source the data and code wouldn't even do it when they already committed to doing it. So it's a massive, massive problem. And so one of the things that we can do is kind of solve that problem by decentralizing the storage of the computational inputs and outputs. And we actually have a pipeline for that if you go to our GitHub. Please feel free to contact me also. We have a pipeline that we're building for that, for like uploading results to Tableland, storing them on things called DeSci nodes, which is like a decentralized science publication platform where you can upload like code figures, literally everything around scientific objects. It's creating a research object rather than just a PDF. And so we basically have a computational pipeline set up for that. So that should speed up a lot of what you're trying to do when you're building on top of this. And so so we can decentralize it, and now we can reproduce it. And so we can also make sure that if we're handing out tokens for contributing, we can actually make sure that it's verifiable and people aren't cheating. Right, which is really, really important. And that's my background. It's a mechanism designed for optimistic compute. And so if anybody has questions about that, feel free to ask me as well. And so, the central task that you have is to find the best use of latent compute that you possibly can, primarily for scientific discovery and or the public good. So think about maybe finding the cure for cancer, but it could be analyzing satellite imagery for carbon credit markets. It could be literally anything that you can think of, just as long as it's valuable, as long as it's a good idea, and as long as it's valuable and has and ideally long term is the type of thing that can generate revenue. It doesn't have to, especially now because very luckily we're in an age where retroactive public goods funding is becoming more common. So it doesn't even necessarily have to, because it doesn't have to become intellectual property or something like that. It can be out open in the public domain, and we can use retroactive public goods for funding it. So those aren't the only types of computations that you can do. There are things that really have. It's very hard to see where there are revenue streams, and we would definitely still reward that if it was a really good idea. But for those of you who would be interested long term in building these kinds of projects, this is something that we're doing at CoopHive. So we're part of our business model is to take this marketplace that we built at Protocol Labs and make it totally free to use. So that means no fees, pay in any currency that you want, deploy any chain that you want. So it's like a total public good marketplace. We're not really putting up any barriers to using it. And part of our business model is to basically incubate distributed computing projects on top of this protocol. And so, and then we start creating fascinating, robust crypto-economic systems around science, which is becoming very, very. It's kind of a bubbling topic, I'd say, in crypto. It's a bit more on the DL, but like the reality is that like it is inevitable because it's so many of our capabilities are perfect really for decentralizing science. So yeah, that was a lot of side tangents and side comments. So yeah, I guess does anybody, Yasin, or does anybody in the audience have any questions?
Yes, there are a couple of questions that have been shared with us. You can check them out in the questions tab on your bottom right, or I can read them out to you. I don't know which one.
Okay, I'll see them. I can read them out. So Zaremba, so most Web3 platforms that say they will allow people to use their spare computational power end up with providers who have custom-built computational resources. How can CoopHive be different? That is an excellent question. That is a really, really good question. Especially because we were with the Protocol Labs, and Protocol Labs built Filecoin, and we it's kind of quite well known that they had a really robust crypto-economic incentive system for onboarding a huge amount of storage and a huge amount of compute. The problem that they ended up with was that they have a huge amount of compute, but there's nobody there to buy it. And so that problem has been like slowly we're reaching an equilibrium now, because now there's like less storage on the network and more buyers. So like that problem is being fixed, but originally it was kind of like a serious crypto-economic problem. So we're taking inspiration from like BOINC is the classic example, Berkeley Open Infrastructure for Network Computing. People will go like use like old laptops like from schools. They'll collect stuff that was going to go in the dumpster or some e-waste thing. They'll use old phones. We can run right now any Docker or WASM image. So we were built originally as an incentivization layer on top of a distributed computing platform called Bacalhau, which was also built at Protocol Labs. And the goal of Bacalhau was basically run any Docker or WASM image anywhere from an IoT device all the way up to a GPU server. And so it was really supposed to be able to run anywhere, including mobile devices, including laptops, all that stuff. To be clear, so we of course naturally have support for Bacalhau. We want to like kind of make, in the same way we want to have no fees and no token lock-in. We also want to be able to run jobs in any of any job spec. Really, ultimately, it would be great to have integrations with other distributed computing networks, just because. And this is kind of another tangent, but I'm quite skeptical of like marketplaces as a moat. It doesn't make any sense. We're all these Web3 distributed computing platforms are all like replicating a lot of work. And this does not make much sense, but that's a totally different topic. So yeah, we can run any Docker WASM container. We can size jobs accordingly to how to fit like going back. Oh, this might answer your question. In the job and resource offers, you can specify what kind of resource offer you're providing. You can specify I'm only providing on my laptop 2 gigs. And half a core, 2 gigs of RAM and half a core, and that's all you're going to get. And whatever buyers are out there. So there's like it's completely modular in that sense. Any node can offer up any amount of computational resources, and any node can buy it if it fits their job spec, basically. The people who ended up with their custom-built computational resources, those are people who were like. And we're talking about miners here, basically, right? Like we're talking about GPU miners for Ethereum or storage miners for Filecoin, and that kind of stuff. That was in a large part due to the crypto-economic incentives of like those networks. We would have something similar in the sense that where the state space for us, the state space of computations, is effectively anything that could be valuable in the future, but isn't necessarily valuable now, which is enormous. The state space is practically infinite for the types of tokens that we can create, and so it could be worth it for people to create their own mining rigs or use existing mining rigs for it. But it also could be worth it just to like contribute your laptop or desktop, there's nothing stopping you, and there's nothing stopping you from making money from it. So in that sense, it democratizes things a lot. Now, obviously, the people with more computational power will end up getting more tokens, but that's kind of just the name of the game, basically. Like, I mean, you can design alternative systems, but then you start getting into identity problems and Sybil resistance problems, and so like at least for right now, it kind of makes sense to have like rewards scaled in manually. So yeah, well, my first question is, did that answer your question? And while waiting for that, I will answer the second question was, how does mediation change the dynamic incentive structure as compared to other decentralized computing platforms? That's a great question. So there's kind of three main classes of verifiable computing. So one is cryptographic methods. So zero-knowledge proofs, multi-party computation, fully homomorphic encryption, etc. So that's an entire kind of class of computations that actually fully homomorphic encryption is a bit different, but like let's say certainly zero-knowledge proofs and MPC, they're kind of centered around like if you do know you're getting the right result. With a zero-knowledge proof, assuming the math is correct, you know you're getting the right result, right? The second method are secure enclaves, so trusted execution environments. Again, the idea there is ignoring all of the potential hacks. And which are being patched up slowly over time. The idea is, the computation is being done correctly and it's private, right? Same thing with zero-knowledge proofs. For us, because we're dealing, and so we do verification via replication, which is basically optimistic verification. That is mostly because that is what we were tasked with building at Protocol Labs. That's what we were getting paid to build, was a network with optimistic verification. And because we're primarily dealing with entirely public data sets, right? So if you think about like when people were looking for the spike protein for COVID, all that stuff was public. Making a three-dimensional map of the Milky Way, looking for aliens, all of this can be public. So kind of privacy concerns aren't really a problem here. Although of course we can integrate with secure enclaves and zero-knowledge proofs with like other protocols and so on. That's kind of on the long-term roadmap. But we'll set that aside for a moment. I say that because just to give like a big picture overview of like, okay, where we are in the third category of verification, which is just verification by repeating the computation. And we're going to ignore issues of determinism for now because those can get a bit, that's a whole rabbit hole. So how does mediation change the dynamic and incentive structures? Okay, so it really depends on what other decentralized computing platforms we're being compared with. But I would say this. I mean, the purpose of one of the purposes of our protocol is to drive the number of replications down to one, right? So in blockchains, you have you have Byzantine fault tolerance. You're supposed to have the more replications, the better, right? The problem is the more replications, the higher the cost. Same thing with zero-knowledge proofs. Like they have a massive overhead, right? And so if you put that overhead in computational costs or even the financial costs, it could be 50, 100, 1,000, 10,000 times higher than computing it compared to bare metal. Some other older verification by replication protocols also had a similar problem. They would have even two replications. Is that this is doubling the cost relative to bare metal, relative to AWS has a markup, and so do the other big cloud providers. But ignoring that for a moment, you're just doubling the computational cost relative to the network itself, actually, by doing the computation twice, right? So one of the purposes of our protocol is to drive the number of replications down to one using crypto economics and game theory, which is basically you put up a stake, you put up collateral, if you get caught cheating, you get slashed. The details of that can get very, very complicated. Actually, in the docs that I linked to, you can read more about there. I have a bunch of writings up there. I gave a few talks on YouTube I gave as well. The mediation basically acts as a verification mechanism, and that verification mechanism ultimately is designed to make sure that all that there's an incentive that all the computations are done correctly, and two, to drive the number of copies down to one, basically, in all situations. In terms of incentive structure, in terms of the dynamic incentive structure, I mean, there's all sorts of, it depends, you're talking about the market making, you're talking about the price and the scheduling, it changes a lot, but the kind of overall big picture idea is that it's just supposed to stop cheating. It's supposed to encourage nodes to behave honestly, That's like the overall that's the overall goal. And not all other distributed computing networks have that. So there are some like big networks that I can think of that which are great, but like they don't have any verification at all. And then trust execution environments also have a bit of an overhead. It's not massive, but like actually optimistic verification can get better than trust execution environments because you're computing on bare metal. You have to put up higher collateral and so on. That's the purpose. Yeah.
Perfect. Do we have any other questions in chat? Zomas actually does have a lot more questions, but there's still more to come.
Oh, I have. Oh, yes, I remember saying that they have more questions. I'm also carrying a tiny and wriggling human. Oh, I can wait. I have actually. Well, you actually have the original call was scheduled for now, so actually I have this time slot for now. Yeah.
Right.
Yeah.
Cool. Well, if there are no other questions, we can obviously wrap up. But yes, Levi, thank you for sharing all of that documentation. We'll make sure to make it available to all of the participants during the hackathon. We'll also, for those of you that are watching the recording, all of the links will be shared inside the Hacker Pack, which all of you have received. It's a collection of all the important links that you will be needing for the duration of the hackathon, so you can end up building something interesting. What's the best way to contact with follow-up questions? Yeah.
Probably Discord. So
yes.
Discord.
If I can add, there's a dedicated section on our Discord for each and every of the sponsors and all of the bounties. So if there's any bounty-specific questions that you might have, feel free to post on Discord, and we'll bring it to the attention of all the sponsors. That might be Levi or any of the other ones that you would like to contact or build for.
Yes. Okay. So I'm gonna just post that. I think this should be the right link. I think that should take you to the correct group chat. I hope it does. For the CoopHive, the CoopHive zone event. Yeah. So basically, the Discord Encode Club CoopHive zone, and then you can also my username, my Discord user, if you want to DM me is. Although please do also message on the public Discord so other people can see your questions. So to help the community as well. So that, and then that's also my Discord username. You can find me there. Actually, I'll probably just say hi in there. Yeah, once I move my screens and stuff. But yeah, cool.
Perfect. As Levi said, everyone that is looking into building for CoopHive, also please sorry for mispronouncing it twice. I always because I think I said it CoopHive. It's CoopHive. So all of you that would like to build for them, make sure to post your questions on Discord. We'll make sure to bring them to the attention of Levi or anybody else on their team, and give you all the ample support that you might need. Perfect. Levi, any closing words? For everyone.
No, yeah, I'm excited. I wish everyone luck. Yeah, feel free to ping me or any of our team members. Happy to help.
Amazing, thank you. I hope everyone enjoyed the workshop. It was really, really nice, and we definitely not needed any slides whatsoever. So it was again amazing content. For those of you that will be asking for the recording, we will make sure to make it available tomorrow morning. And you will be able to find it inside the Hacker Pack as always. So yeah, thank you all for being here. Hope you enjoyed it as well, and see you all tomorrow for another amazing batch of workshops.
Yeah, thank you so much, everyone, and
see you. Thank you for coming. Bye bye. Have a great day, everyone.